based on the and it's based on the capybara. And if you want to go on YouTube or whatever and look for capybara videos, they're just as fun as cat videos. So, Lucas?
Yes, hello everyone. Yes, I definitely do recommend people going online and searching for capybara videos. These are the best. If you ever come to South America, you can even interact with capybaras in the wild. You just can't touch them because they have they could have some sort of deadly disease. So I don't recommend petting them, but watching them from a distance is definitely safe. Hello everyone. My name is Lucas. Today I will be presenting to you CapRX, a guide to early adoption. This is, like Steve said, this is a multi-path system for CarpetX. We are close to having a minimum viable product, and today I will show you a little bit of what goes inside CapRX, and at the end, we are going to have a live session where I am going to show you a notebook teaching you how to implement a wave toy using our new multi-path system. So, what does CapRX mean? Where does it come from? Well, this is an idea that I had. This code is developed by me, Lucas, and by Eric Schnitter, who just did the presentation on CarpetX. So the idea for the logo was to pick the largest rodent in South America and the largest rodent in North America, and have the two of them creating a path system together, which is definitely very cute. And this is, as everyone knows, this is the most important part where when you are developing a new software project is to pick a nice logo and a nice name. This art was commissioned by a friend of mine. I have his Instagram handles if you're interested in checking out his art. Okay, so let us start. What is a multipath system? Well, multipath system essentially comprise in covering a simulation domain with multiple coordinate system. So don't be scared about the math here. We're going to go over that in a second. By construction in general relativity, it is very natural to cover a space-time manifold, which is the object of our study, basically, with multiple coordinate charts, right? If you study general relativity, you know that a manifold can be covered with one or multiple coordinate charts, and the physics of what you're studying does not depend on the coordinate charts that you're using to cover your manifold. So what this diagram here is showing is essentially you have a space-time manifold, and then you have a submanifold where interesting physics is happening, and you want to study things here, right? You're going to cover this submanifold with a global coordinate system, which we're calling here in this diagram phi g, right? And we're going to subdivide this phi g with further coordinate charts. We're going to subdivide this global system with multiple coordinate pieces covering each different part of the domain. And the important part here is that you have ways to go from the local patch coordinate system to the global patch coordinate system, and from the global patch coordinate system to the local coordinate systems, right? So you have a way of going back and forth through local and global coordinate systems, and you are all these coordinate systems together are describing your manifold of interest here. Notice that we have this additional global coordinate system here. This is not strictly necessary if you are developing a multipath system, but this is what's often done in implementations. This is what it is done in the current implementation in Llama, and this is what we are doing in CapRX as well. Right, so basically the takeaway message here is that we're going to cover our simulation domain with multiple pieces, and each piece is going to be embedded in the global coordinate system, but the transformations from local to global and global to local are known, right? So here in this diagram, each piece of the puzzle is a patch, right? You have 9 local and 1 global coordinate here, right? So you can go from each of these patch pieces to the global coordinate system and back, okay? But why do we want to do this? Why do we care? Why do we want to subdivide our domain using multiple coordinate systems? Well, let's start with some motivating examples. We'll do a back of the envelope calculation here, right? Let us imagine that we have a 2-dimensional grid with dimensions delta x, delta y, and grid spacings hx and hy, right? Then the number of points that we're going to have to store in memory is given by this expression. There's nothing very difficult here. Let us suppose that we decide to increase the resolution of this grid, right? So we're going to divide hx and hy by a delta x and delta y factor, right? How does the number of points change? Well, it changes according to this formula. So if you take a look at this right-hand side here, we are comparing this to the situation on the left. You're going to see that the number of points you need to store grows with delta x, in order delta x, delta y, right? It's a product. If these two were the same, it would grow in delta squared order. So this is a very high increase for when you decide to increase the resolution of your domain. Something similar happens if we decide to increase the size of our domain, right? So here in this situation, I have a two-dimensional grid with extension big delta in x and y, and grid spacing h in both directions. And I decide to increase this domain here by a small delta, right? Keeping the same resolution. So how does the number of points change? Well, it changes according to this formula. Again, you see a order delta squared factor here, right? So what happens is if we decide to increase the resolution or increase the size of our domain, the number of grid points that we're going to have to store in memory greatly increase. And to get an idea on how bad this becomes, if you go to a three-dimensional simulation, which is what we do most of the time, let us suppose that we have a cubical grid. Each side of the cube, I'm labeling it delta, so equal dimensions delta on each side, and equal grid spacings of h. Let us assume that our computer uses 8 bytes per double precision floating point number, right? So let us compute how much memory do we need to store a single grid function in a typical grid. So for instance, let us consider that we have a fixed grid spacing of 0.1, and we're going to change the domain size from 100 to 400. We're going to double in each iteration here. We go from 8 gigabytes to 64 gigabytes to 512 gigabytes of memory if we decide to double the size of our domain in each iteration, right? And something similar happens if we decide to change the grid spacing, right? So let us suppose that we have a fixed sized cube, which we're choosing delta to be 100. If we increase the grid resolution if we double the resolution in each iteration, so you go from h from 0.1 to 0.025, again, we need 8 gigabytes, 64 gigabytes, and 512 gigabytes of memory to store a single grid function, right? And you might say, well, then just don't increase the domain size or just don't increase the resolution. That's not really an option depending on what you're doing. And this is what we'll be discussing. Why do we want to have large domains, and why do we want to have high resolution? Well, high resolution should probably be obvious. We want high resolution because we want to capture physics with accuracy. But domain sizes are also an important thing, right? So simulations, as we know, cannot extend to infinity, and eventually you're going to have to impose some artificial outer boundary condition in your simulation. In fact, Li Wei in the next talk is going to be talking about such boundary condition, such outer boundary condition. And there are many ways that you can implement these outer boundary conditions, but none of them are perfect. They can be very good, but none of them are perfect. So for instance, what NeuRAD-X does is it simulates a transmitting outer boundary. So if you have a gravitational wave, for instance, and it reaches the outer boundary, that outer boundary simulates the gravitational wave leaving your domain. But that is not a perfect boundary condition, and there will be some spurious reflections that come back from the outer boundary to inside your simulation domain. So let us suppose that we're decided that here we want to measure the gravitational wave signal of a binary black hole merger, or merger is close to the origin, right? And as the black holes spin around and merge, they're going to emit some sort of gravitational wave here that during some extension of time, right? Let us suppose that we also are going to place our detector or simulated detector here at some distance RD from the binary black hole merger. And we are going to place our outer boundary at some radius RB. We want to have our measurement happening here in such a way that the incoming data from the outer boundary does not interfere with the measurement that we're trying to do, right? So essentially, we want these spurious numerical reflections to not infect or contaminate the physics that we're trying to the physics that we're trying to measure here. So ideally we want to place the outer boundary as far away as possible from our detectors and from where physics is happening. So this is a justification why we need large domains. And an easy way to get rid of that is to consider the same situation now using a spherical, here in this case a circular, because we're looking at things in 2D, right, grid. So the advantage of spherical coordinates is that the radial resolution and the angular resolution are decoupled. This does not happen in the Cartesian case. So if you want to increase the resolution of the radial direction, you can simply do it. You don't have to increase the resolution of the angular direction. And often what we want to do is to increase the resolution of the radial direction, and we want to push the outer boundary radius as far away as we possibly can. So because we just have to change, because we're just changing a single dimension instead of 3, we don't get that explosive behavior on memory requirements, right? And so here, the thing is, the multipath systems, they allow us to use coordinate systems that are adapted to the problems we're trying to solve. And this allows us to use fewer points. This allows us to save memory. This allows us to increase runtime performance and other things such as having, natural outer boundaries, natural inner boundaries to the problems we're trying to solve, right? So this little cartoon here illustrates this using Cartesian is not always the best thing we can do. Okay, but if you noticed so far, I've only praised using spherical coordinates, basically. I'm just telling you that Cartesian coordinates are not the best thing we can do. Why do we actually need multiple coordinate pieces? Why do we need multi-patch? Well, as many of you probably know, spherical coordinates are singular in the coordinate axis, and general relativity had singularities enough, so we don't want to introduce new singularities using different coordinate systems. And a way to avoid that is to describe the surface of the sphere using not only one coordinate system, but using 6 coordinate system. Right? This idea here was first proposed by Jonathan Thornburg in a scheme that he proposed for his apparent horizon finder. So the idea here is that you imagine first a cube. Cube has 6 faces, and you imagine that this cube is a sort of a rubbery, malleable cube. And somehow you're going to blow air inside of that cube. And as that cube grows, it's going to be slowly deformed into a sphere. And each of the faces of the original cube are going to become these spherical caps here, right? Each of these spherical caps describes a section of the sphere. But in the end of the day, if you join all of these, you are describing the whole surface of the sphere without introducing any new coordinate singularities, which is what you actually want. So this coordinate system, it's called Thornburg 6 in Llama because Jonathan Thornburg was its original proponent. These are the coordinate transformations that you use to go from Cartesian to patch local coordinates. They are based in these 3 angles, mu, nu, and phi, right? And this is a 2-dimensional cut of the same coordinate system, right? So you got a spherical inner boundary and a spherical outer boundary. Here we got 4 of the 6 patches. You have to imagine that there is a patch on top and a patch below this image, right? And one advantage of this is these are good for evolving single black hole systems. So, right? So for instance, you can simply place your inner boundary inside the event horizon of the black hole you're trying to evolve. And basically you turn off the evolution inside this inner boundary and you sidestep singularity problems, right? This is a good coordinate system for this sort of problem. Okay, an evolution of that would be the K coordinate system or the 7-patch coordinate system, or there are many names in the literature that you can find this. We're naming it the K coordinate system for historical reasons. The K coordinate system is basically Jonathan Thornburg's 6-patch system, but now instead of having a spherical inner boundary, we have these Cartesian inner core. And the thing here is that the Cartesian inner core is continuously joining with the patches, right? So the spherical patches go from a flat surface to a spherical surface, and they are continuously joining. If you notice here, you have a kink between the coordinate lines. They're not a smooth junction, but they are a continuous junction. Okay, and what's the advantage of this is that we can evolve systems with less symmetry because we have a Cartesian core. For instance, let's suppose we're doing a binary black hole or binary neutron star or any combination of that merger, right? You can place in here freely without having to worry about that, central spherical symmetry and have that work. You can also add adaptive mesh refinement here very easily to this Cartesian grid, right? And then the idea is you put the physics that you're interested in this Cartesian core, and then from the flat surfaces to the outer boundaries, you're going to add a large spherical buffer zone where you're going to measure gravitational waves and add your outer boundary and so on and so forth, right? This is so here we have the coordinate transformations that define these patch systems, right? They go local coordinates here. Patch local coordinates are labeled as A, B, and C, and Cartesian global coordinates are labeled as X, Y, and Z. And it's important to note here that we are choosing each patch local coordinate system to range from -1 to 1. Okay, the most obvious problem that arises when you introduce multi-path systems is when you have interpatch boundaries, right? So we are basically covering our domain with more coordinates, and between each patch, we're introducing a new interpatch boundary problem, right? We have to decide how we are going to communicate information between different patches considering the interpatch boundary. So here in this diagram, we are going to study 3 different ways of doing this. Suppose that this green bar here is the patch boundary, the place where the patches touch. Here we have a left patch and a right patch. Filled boxes and circles here represent grid points, and non-filled empty boxes and circles represent ghost zones. So we have basically 3 approaches in what we can do. We can have our patches touch. That means that the first point in the left patch and the last point in the right patch coincide exactly in the interpatch boundary. We can have exactly the same situation as before, but extending it with ghost zones. So the first point and the last point in the patches coincide, but we extend them with extra ghost zones. And approach number 3 is to have the patches overlapping, which means that 2 patches are going to cover the same space-time region twice, right? You're going to so basically we have different patches covering the same global points, right? So this is what we're depicting here, and we add ghost zones to that. So how do we treat boundary conditions in each of these cases? Well, for case 1, where you have just touching patches and no ghost zones, you do characteristic exchange. Characteristic exchange is basically decomposing your partial differential equation in this boundary, right? And analyzing the flow of information that goes from one patch to the other patch. So in the right patch, you got, the characteristics from the right coming to the left. You're going to have to store them to the left point in the left patch, and characteristics coming from the left to the right, you're going to store them in the first point of the right patch. Characteristic exchange is probably the best thing you can do mathematically, but it's not easy. It's easy if you're evolving the wave equation, which involves, decomposing your partial differential equation in a certain way to determine what these characteristic variables are. While this is easy to do in simple systems, it is not as easy to do in more complicated systems such as the BSSN equations, right? So this is why our first implementations are supporting approach number 2, which are touching patches plus ghost zones. Now here we do one-sided interpolation onto the ghost zones, right? So we fill these ghost zones, these extra points here, using interpolation from one patch to the other patch and from this patch to this patch. This is easier for simple to implement. They don't have to worry about computing characteristics, and it's much easier. It's much more familiar to people that have used Llama. And approach number 3, which is what Llama does currently, is to use interpolations onto the ghost zones, non-one-sided interpolation onto the ghost zones with the overlaps, right? Using patch overlaps, we don't need to make the coordinate transformations exactly match or be continuous at the boundary. So, this is easier from the point of view of the person that is implementing the patch system, but it has some disadvantages, right? So this is a typical grid that we use in Llama. Go ahead. There is questions? Yes. Yes, please go ahead.
Can you go back?
Of course.
So for these touching patches,
Mhm.
we can do it at the patch boundary, but we also have interprocess boundary inside each patch, right? So I wonder if we can also do this touching thing inside a single patch. Because the ghost point inside that patch is not touching. I mean, you don't. The connection between two processes is not like this, right? I think you need to come up a new coordinate system. The way in general the ghost point is not like this touching patches, right? You don't share. The boundary is not at the grid point, I think.
Right. I think what you mean is, there are two different things maybe at play here. One is the interpatch boundary, and one is the interprocessor boundary. And I think I'm going to say what I think you're saying, and if I'm not correct, you please do correct me. This diagram here, these pictures, they are not considering interprocess communication, because then it would be a very complicated diagram to try and explain to people what we're doing in the interpatch boundary. So I think you could consider for these diagrams that the patches are living in single process, but if your patches are split across multiple processes, then of course, like you said, you'd have to consider the communication between them, and that is a more complicated problem, and that is a problem that the interpolator has to solve. But in principle here, what we want people to understand is how we are treating the communication of data, how data flows between one patch and the other patch independently, or of where these patches are residing, if it's in a single process or in multiple processes. Is that clear? Did that answer your question?
Sorry, let me try to ask again. So can we do the same data flow between interprocesses using the same way you just showed?
Oh, okay. So you mean using this, or
maybe the first one, yeah.
Okay, right. So doing characteristic exchange, yeah, I believe so. Yes, I don't think there's nothing stopping you from doing that. The problem here is that you have to decompose characteristics. You have to decompose your partial differential equation to find its characteristics, and that is not easy if you're trying to solve a complicated system. Characteristic exchange, I've never seen it used for interprocess communication. I think it can be done. What I have seen it used for is to applying outer boundary conditions. So if you want to have like a true, transmitting outer boundary, the way to do it is to, do characteristic decomposition and to impose in the outer boundary that your left going characteristic is 0 and your right going characteristic goes through, right? So basically you want to kill a specific characteristic in the outer boundary. I have never seen people use that for interprocess communication, but I think it could be done. I just don't know if there are any advantages in doing so.
All right, thanks.
Right. So continuing on, this is the grid as we have it in Llama today, which it uses approach 3, which is overlapping plus ghost zones, right? So this is the same thing as the cake patch, but you have the spherical patches overlapping not only amongst themselves, but overlapping with the central Cartesian grid. And this is very easy from the point of view of the coordinate implementer and from the point of view of interpatch boundary treatment. It means that users don't have to worry too much about this. But there are some problems when doing this. This is why we want to have the patches touching instead of overlapping. For instance, if you are doing hydrodynamics, you want to have a finite volume code, and you want your cells to be, in pretty specific places, and you want to know exactly which cells are connected to which and how the numerical fluxes go from one cell to the other, right? You can imagine trying to do that in such a situation here. This is not going to be very fun. If you're trying to do hydrodynamics in this sort of grid. Whereas if you have touching patches, you know exactly what's the connectivity of each grid cell. Apart from that, this is not as efficient as it could be. If you look at the center here, there is an excess in coverage, right? So there is the excess volume of a cube inside a sphere, right? That's being added here, which doesn't need to be added. So what about CapRX? Well, CapRX has a few aims that we're striving for. The first one is ease of extensibility. I would really love that people implement their own coordinate systems, their own crazy and fun coordinate systems, right? Because while that I think it's doable in Llama, it's not very easy, and we're trying to make this as easy as possible. And for that, we need rich documentation. We have some documentation, but of course this needs to be vastly improved in order to help people to add in the ease of extensibility, ease of use and integration existing codes. Llama is very easy to use and very easy to integrate. We want to be as easy as Llama is to use and to integrate. We want to add the customizable boundary treatment. So far, we have only implemented type 2 because it's the most useful for production people. And then we want to also support type 1, which is characteristic exchange, which is difficult, but we want to support that. And we want to support rigorous unit testing of the patch systems, right? So the patch systems we have implemented so far have a rigorous unit testing suite that tests the coordinate transformations, Jacobians, and so on and so forth. So currently the coordinate systems we have are the good old Cartesian coordinate system, the cake coordinate system, and these two here, which are used mainly for debugging. The swirl coordinate system is a Cartesian cube with the outer boundaries fixed, but the interior twisted 90 degrees, right? So this is an extreme example of coordinate distortion, useful for debugging. And the 2 cubes patch is 2 cubes that are touching, that have a common interface. The flat of this interface is the top of this interface is flat, but the bottom is shaped like a triangle, right? So we pinch the junction of the cubes in a single direction until you have something distorted in the form. This is very useful for debugging. Missing features. Well, we're very close to delivering minimum viable product. If you remember last year, the presentation that I gave, we weren't able to synchronize the points. We weren't able to, fill the grid with initial data, then synchronize to the goats and do an evolution step. We weren't able to do that. Now we are. We are able to evolve the code for as long as we want, which is a win. But we're still facing some interpolation bugs in the interpatch boundaries, and I think we're going to be able to see that in the demonstration today, right? But after we fix these bugs, after we fix these interpatch boundary interpolation kinks, I believe that we can run a large-scale evolution test with the standing wave, and after that, people can, start using that in their codes. So now I would like to show a demonstration. I believe we have time for that, so let me stop sharing this and share our notebook. Now I'm going to go over the notebook. If there are any questions or anything that you would like to say, please interrupt me. So here we are going to do the implementation of a scalar wave equation using multi-patch, right? So we start by using the notebook magic that we have in all of the other notebooks. And this notebook here is going to assume that you have been through the Cactus tutorial, so you have a working Cactus distribution in your user folder. The CapRX arrangement of thorns can be found in this GitHub link, right? And if you wish to include it in your local licensing toolkit distribution, you just simply have to add these lines to your thorn list. The CapRX arrangement comes with Multipatch, which is the main actor here, which is the multipatch system responsible for defining the coordinates and so on and so forth. Multipatch Wave Toy, which we'll be basically using today and looking today. The point of the store needs to be a wave toy that people can look at and figure out how to do their multi-patching. And Test Multipatch, which is an internal testing tool that we use for debugging purposes mainly. So what we'll be doing today is we'll be using the formulation of the scalar wave equation that's presented in the creating a new thorn. And we'll consider u to be your dependent variable. In Cartesian coordinates, this scalar wave equation becomes this. Everybody is familiar with that, right? Here we're choosing the wave speed to be 1, and we're going to do the standard time order reducing, right? So we're going to turn this into a system of 2 coupled partial differential equations, introducing a variable called rho, and this is the evolution equation for u. This is the evolution equation for rho. This is the system we'll be evolving. Now, as I mentioned at the beginning of the talk, we have local and global coordinates, right? So following the tradition of multi-patch codes in the Einstein toolkit, CarpetX stores grid functions with respect to the global Cartesian system. This has several advantages and facilitates doing things a lot. But the patch local coordinate systems are the only coordinate systems that define a uniform grid. So when we approximate this by finite differences, we are implicitly assuming that we are discretizing this in a uniform grid. So we are implicitly discretizing these quantities here in local coordinates, but we are storing the grid functions, u and rho, with respect to global coordinates. This means that we're going to have to project or derivatives from local to global coordinates, right? And Llama provides an easy way of doing that. If you look at the thorn list, there is a global derivatives thorn. That thorn does that projection for you, and it can even apply summation by parts operators. We don't have that yet for CapRX. We probably will have that someday, but this is an early adoption guide. So unfortunately, these projections have to be done manually today, and I will show you how that works. So let us suppose that we have a global grid, right? Global coordinates x, y, and z, and we have local coordinates a, b, and c. The first derivatives can be projected from local to global space as this, right? So this is simply the chain rule applied to the derivatives, right? So the derivative of a grid function with respect to x, y, and z is the derivative with the grid function with respect to a, b, and c, projected by this relation here, right? The derivative of the local with respect to the global coordinates, which is also known in other circles as the Jacobian of the coordinate transformation, right? So defining the Jacobian symbol as this, we can compactify that expression as something like that. And we can compactify it even further by saying that derivatives with respect to the global coordinate system are going to have hat, right? So partial hat is a derivative with respect to global coordinates. This is the projection we're going to have to do. We can do this twice, and we can get the same sort of relationship for second derivatives. So if we want to do an even mixed second order derivative here, with respect to the global coordinate system, we're going to need the Jacobians of the coordinate transformations, but we're also going to need the derivatives of the Jacobians of the coordinate systems, right? So defining a multi-patch coordinate system entails that you're going to have to define not only your coordinate transformations, but their Jacobians and the derivatives of those Jacobians. So you're going to have to tell CapRX all that if you're implementing your coordinate system. And CapRX, of course, provides grid functions for that. So when a user chooses a specific coordinate system in Carpet X, it initializes the coordinate grid functions provided by the coordinates X thorn. This comes with Carpet X, right? This is not a part of CapRX. And itself, CapRX has the vertex Jacobians and vertex D Jacobians grid function groups. And these groups are what you expect, the Jacobians and the Jacobian derivatives. One difference here from Llama is that the nomenclature in Llama is a little bit more confusing, and here we've tried to be more explicit. So if you're trying to get, the second derivative of b with respect to x and z, you just simply have to pick the grid function that is named accordingly. And in Llama, that was a little bit confusing, and I had to implement this projection manually once, and I got it wrong multiple times because of the sort of naming convention. So this is something that aids users a little bit, we hope. And of course, like I said, currently users are responsible for manually doing these projections from local to global space. In the future, we plan to, streamline this process, but this is what we have. But there is a facilitator, let's call it that. The multi-patch wave toy thorn in CapEx provides a Mathematica notebook in its resources folder. So when you clone a repository, this comes free to you, right? This somewhat facilitates the usage of CapEx by automatically generating CarpetX compatible C++ code for these projections. I mean, there are a lot of tools that can do C++ code generation for CarpetX. I've used Mathematica because it's the thing that I was most familiar with, and it was the quickest for me to do. It's not necessarily the best solution, but it's probably better than nothing, right? So first, in this notebook, users can choose the order of the finite differencing operators that they want to employ, and this assumes that the stencils are centered, so you can choose the order. So in this example, we have chosen second order, and this produces expressions for you for the local derivatives and for I didn't want to do that, for the local derivatives and for the projections of those, right? So for instance, this is a simple example of the output of that notebook. For instance, our grid function is called u. You want to compute the derivative of u with respect to x, and you want to compute
10
second
minutes.
derivatives with respect to that. The code produces the correct, utilizes the correct Jacobians in the correct expressions for you, so that you don't have to worry about it. The rest of the notebook is running a parameter file. We're going to run a quick simulation of the wave and take a look at it, right? So here, the relevant sections are the following. You need to activate the multi-patch thorn, and you need to activate the coordinates X thorn if you want to use CapRX. And multi-patch toy here is our physics thorn. We choose the blocking factors to be 1, right? The blocking factors avoid complications with grid sizes. There is a section 2.10.2 of the CarpetX documentation explains what the blocking factor is. I'm not going to go into detail, but choosing 1 is kind of important here. And then you pass to multi-patch the coordinate system that we want to use. In this case, we want to use the K coordinate system. We set the inner and outer radiuses. We set the number of cells in the Cartesian core and in the spherical region. And we set the initial data to be the standing wave, right? So we're going to evolve a standing wave in Minkowski coordinates using that spherical coordinate system. Here we have some code for submitting the simulation. I am downloading the parameter file from the GitHub repository because the local version is a little bit out of date. So this is why I'm downloading the parameter file instead of using what's coming in the repository, and submit the simulation as we are used to. And visualization is a problem because visualizing the output today with Llama, we would use Visit, but that's not available to CapRX yet. We have to implement our own solution for visualization. And we have provided a Python script called MPX. It stands for Multi-Patch Plotting Utility, right? It's basically used for looking at data and plotting the data, right? So this is a Python script that comes with the CapRX repository that people can use to visualize their simulation. Because MPX uses several libraries, you have to figure out how you're going to set that up. In this notebook, I am just using the -- user option to pip to install the packages I need, right? And here I am calling MPX. This is the help menu of MPX. Currently, we just have a single option, which is plot OpenPMD slice. It looks at OpenPMD data and it plots a two-dimensional slice from that, right? So you have to pass the data file, star name, group name, variable name, a lot of things that you need to provide in order to read the OpenPMD data and plot a slice from that. But here we have some code showing you how to create an animated GIF. So that parameter file I showed you runs for 20 iterations, which is an exact shifting between the minimum and maximum of the standing wave, right? A single period of shifting. Here, this is a bash loop running for the 20 iterations that we just produced, running the MPX utility. Here, I'm asking it to extract the Z slice coordinate, Z equals 0 slice coordinate. This weird string here is telling which of the patch, the true and false. I'm not going to get into details, but these numbers here represent which patches do I want to put in my plot. You can control that. You can just draw 1, 2, 3, 5, or any combination of patches you want. Usually you want all of the patches, but for debugging, it's useful to control that. And these are the results of the program after it runs, right? These are the PNG files for each of the iterations. And finally, after that, we can create a GIF using these 20 PNGs. And here we go. So this is the result. This is a result for a standing wave evolving in Minkowski spacetime using CapRX with visualization provided by our Python tools, MPX. This is a single period of the standing wave shifting. This is a quite coarse resolution, so this is why you're seeing these weird things here. If you increase the resolution, this plot's going to be much, much smoother. I'm using a coarse resolution because this needs to be run quickly in a tutorial server. So, but feel free to play around and to increase the resolution. And see if you can determine where the problem is of our interpatch boundaries. If you can see where the kinks that we don't want happening are happening, maybe you have probably already spot them. But I think this basically concludes the presentation. If the timer is correct, I think there are 20 minutes yet, but
5 minutes.
Oh, okay. So yeah, in this last 5 minutes, I'm open to questions. I'm open to comments. If you are interested, you can always reach me and you can try to help debug CapRX. We can try to help debug CapRX together if you're interested in using it in the future. And that's it. Thank you.
So we allowed 15 minutes for questions. That's why you have the 20. But
Oh, okay.
So we have extra.
Okay.
While everybody was while we were watching the presentation, since I know that this notebook is now ready, I copied it to everybody's account. So you all have this notebook at this point, if you've made an account on the server, and you can generate this same seizure-inducing plot.
I can hide the plot. Sorry, this
No, I mean it looks great. Every time I make a wave equation plot like that, and I put it on the screen. If I leave it on there too long, it starts to get.
Okay.
Questions? Roland.
So, in Kipper, is there currently any support for fluid quantities where you would have to do coordinate transformation of vectors if you go from one patch to the other handle the tensor weights?
So if I understood the question correctly, support for fluid simulations, flux conservation between one patch and the other. Is that what you said? And the audio was kind of shady.
Speak louder, yes.
Okay.
Not even flux conservation, just if there's support to transform components of vectors as you go from one patch to the other.
Oh, okay. We haven't looked into that yet. Our first order of business is getting the interpolator bugs fixed, and then after that we can start thinking about those extra things. But yeah, that's definitely something that we will have. We just have not started working on it yet. This is still more preliminary than that.
Yes.
Great talk, thank you. Have you tried, changing the aspect ratio of some of your patches, like making one dimension a lot longer or shorter than another dimension and see what happens to the Jacobians?
We have done that in the debug patches, the 2-cube patch that I mentioned. That patch system allows you to have different sizes and different resolutions in each of the patches. So yes, we have been playing around with that. You can define the patches as whatever you want. So if you want to define a patch with radially changing, increasing or decreasing coordinates, you can do that. Or if you want to have patches control the resolution independently of each patch, of course you can do that. You just don't do that in the cake patch because, well, it's for production, it's probably not needed. But yes, you can definitely do that. And you can implement a patch system that does whatever you want it to do.
So I have a question. As I'm watching this animation, there's a square that appears in the middle where the cake is.
Right.
I'm wondering, is that normal or is that an interpolator problem?
You see, you're only seeing the square because if you look at it, look at the interface between this peak and this peak here, right? Look at what happens when they shift. They are shifting, but they look to be going to the left, right? So this is the reason why you were seeing the cube, I believe, because the interpolator is introducing a small difference here in such a way that the coordinates here are not exactly matching in the interpolated ghosts. And this is what I have been trying to fix.
Okay, so that is the bug. Okay.
That is the bug. Yes, exactly. That is the bug. You've spotted it. That is the bug. If you plot just a central patch, you would see, just what the correct thing happening. But here you see that little pesky bug that we have been chasing for a while.
Okay, got it. Yes.
So, related, similar to Roland's question, have you thought about conservative interpolation, conserved quantities?
I thought about what interpolation, sorry?
Conservative interpolation or conservative
Oh,
quantity.
conservative interpolation. We haven't done that. We're doing just Lagrangian interpolation. This is the most basic form of the interpolator. But this is something that, of course, we could definitely consider in the future. This uses internally, it uses the CarpetX interpolator interface, which is Eric's domain. He might be more well suited to talk about that. But yeah, I think there has been an interest perhaps of other people wanting to implement different interpolation schemes other than Lagrangian in CarpetX, and then we would be able to profit from those as well.
If I may add
Yes.
something here. So the fluxes between grid cells would not be on the grid points, but in your scheme would be in the line or in the faces between the grid points. And in your patching touch scheme, the faces on one patch or on the other patch would automatically coincide. That is all one needs to ensure is that these faces have the same values on both the left and the right grid. And then the fluxes on the left and on the right grid agree, and then things are automatically conservative. That is, if interpolation is not conservative, and it's probably difficult to do so because the patches, the cells don't quite agree, you still have overall a conservative scheme because you can make the fluxes agree between the different patches. So whatever leaves one patch will enter the other patch. That will be correct, even if the interpolation of any cell-based values would not be exact.
Any other questions? All right, let's thank the speaker again.
Thank you.